it in presentation mode. Do you see it in presentation mode?
Yeah, perfect.
Okay, so thank you very much, Mar, for the introduction. Today at the seminar, I will present you the work that I'm carrying on at the Institute, and in particular in Magnesia Group. This work concerns the development of the thermal part of a new finite volume code in 3 dimensions to study the magnetothermal evolution of neutron stars. And this code is not finished yet, so this work is not finished yet. And so unfortunately for you, I won't show you any new physically interesting result, but I can show you the preliminary stage of this work, some of the preliminary stage of this work, and at least those concerning my part, and tell you what are the new steps that we need to implement to complete this work that are actually very few because the work is almost completed. And I say we because I'm not working on this alone. Clara is working on the magnetic evolution part of the code, and we are also supervised by Daniele and also by Jose Pons of the University of Alicante. And in the last 10 years, Daniele and Jose developed a 2D code for the magnetothermal evolution of neutron star, and our code is the natural 3D generalization of their work. And of course, this work is part of the Magnesia ERC grant, whose PI, as you know very well, is Nanda. And I want to start with a brief overview about neutron stars. As you know, neutron stars are generated after the gravitational collapse of the core of a massive star. I'm talking about a progenitor star with the 0 main sequence mass between the 8 and the 20 or 30 solar masses. They are very extreme objects. Indeed, they are compact objects which encloses a mass of that ranges between 1 and 2 solar masses in a spherical volume of radius that range between 10 and 30 kilometers. And they have a very fast rotation of the order of that range from 1 milliseconds, from a few milliseconds to tenths of seconds. And they are also the strongest magnets in the universe, with a magnetic field of the order that range between 10 to the 8 and 10 to the 15 Gauss. And from an observational point of view, the neutron stars emit electromagnetic radiation all over the electromagnetic spectrum, and they have different sources of energy. For example, standard radio pulsars extract their as a ultimate source of energy the rotational energy or their rotational energy, which is transferred to the magnetospheric plasma, which then radiates from gamma ray to radio, from radio to gamma ray. And then we have other neutron star with emits thermal luminosity from their hot surface in X-ray mainly. Some other neutron stars accrete, and in some other neutron star, the ultimate source of the ultimate energetic source is the decay of their very strong magnetic field. And here I show you these different classes of neutron stars in the so-called PPdot diagram. This is a diagram which is very important for neutron star astrophysics. In the x-axis, we have the period, the rotational period of the star. In the y-axis, we have the period derivative. And as you can see, different different classes of neutron stars, clusters in this diagram in different regions. And in particular, in the top right corner of the diagram, we have the magnetars, which are young neutron star with very strong magnetic fields. Then we have some thermal X-ray isolated neutron star the radio pulsars, the millisecond pulsars here in the opposite part of the diagram. And basically our code target mainly this neutron star here, which have a very intense magnetic field. And for our work, it's very important also to discuss the structure of the internal structure of a neutron star. Neutron stars are almost a perfect sphere. Their deviation from spherical symmetry is very low, and so basically the mass and the chemical composition distribution is almost spherical, and we can think about them as composed by spherical layers. From the most exterior, we have the ocean, or the envelope, which is in a liquid phase and can be composed either by light or heavy nuclei. Then we, going toward the center, we find the crust with a depth of more or less 1 kilometer. The crust is divided in outer and inner crust. The outer crust is formed by a Coulomb lattice of heavy nuclei plus a relativistic sea of relativistic degenerate electrons. And going toward the center, the density increases, which makes the electron capture more favorable, and so the nuclei becomes more and more neutron rich, until we arrive at a certain point at the density, which is more or less is of the order of 10 to the 11 grams per centimeter cube, where the neutrons start to be expelled from the nuclei, and here the inner crust starts, where we can find also free neutrons. And then we have the core. The core comprises the most of the radius of the volume and the mass of the neutron star. It's composed by neutron and proton in a superfluid and superconductive state. We can find here also, of course, electrons, but also muons. And we can expect to find hyperons, and especially in the innermost part of the core, it is speculated that the matter can settle in a very exotic state, such as a quark-gluon plasma or a pion or chiron condensate, but this is not clear. And so, why is so important to study the magnetothermal evolution of this kind of star? Well, first of all, because magnetothermal evolutionary models are able to account for the phenomenological diversity of different classes of neutron star, the one that I showed you before, and to link them within a unified evolutionary path. And why we need the 3D code? Well, because we know that even if we start with axisymmetric initial condition, provided that they are realistic, and probably they are not, the magnetic field evolution is expected to give rise to 3D modes, and so the axial symmetry it will be broken. And then we know that the 3D evolution leads to the formation of hotspots on the stellar surface, and these hotspots are responsible for a modulation in the thermal emission of this star with the rotational period, because these hotspots are periodically eclipsed while the star rotates. And so this kind of models allows a link between what we actually observe and the internal configuration of a neutron star. Okay, what actually we actually do when we talk about the magnetothermal evolution is to solve two equations, so to the partial differential equation. The first one is an equation for the magnetic field evolution. The other one is an equation for the temperature field evolution. And this basically is the induction equation in electron magnetohydrodynamic, while this is an equation of energy conservation. As I said before, my work deal only with the second equation. So for the rest of the talk, I will talk only about the second part, and all the simulation that I show you have the magnetic field fixed, so not evolving. And so in the second equation is quite simply to be interpreted. For example, the first term is the variation of temperature within a volume. Cv is the heat capacity per unit volume, so it's basically the thermal inertia of this matter. Then we have the flux of heat through the volume boundary, and then we have the source or the sinks of heat inside the volume. Now, this equation seems independent, but they are actually coupled, of course, in these three elements. The magnetic diffusivity depends on temperature. The flux is altered by the presence of the magnetic field, and I will describe you how. And then we have also the source. Here, the source of it are basically due to Joule dissipation. So basically, which depends on the current, and that depends in turn on the magnetic field. And then we have also a weak dependence to the magnetic fields also on the sinks. Here, the sinks of heat are the neutrino process, mainly since the neutron star is transparent to neutrinos. So when a neutrino is emitted inside the neutron star, it flies away and the energy is lost. So if we switch on, if we insert a magnetic field, we allow for new neutrino emission process, such as a sort of synchrotron neutrino emission process, but this is a minor effect actually. And okay, I want to focus a bit on the effect of magnetic field on the heat conduction, because it will allow us to interpret the result that I will show you. Here, we can write the heat flux as a sum of three contributions: a contribution parallel to the temperature gradient, a contribution parallel to the magnetic field, and a contribution which is orthogonal to both of them. Here, notice that B is the versor of the magnetic field, so it's normalized to 1. An important here, this number is the thermal conductivity in the direction perpendicular to the magnetic field, while this is the conductivity in the direction parallel to the magnetic field, which is equal to the conductivity in the isotropic case. And they are in a relation that can be expressed by this this approximated relation, sorry. So the ratio between the two is equal to 1 plus this number, omega b tau square. I will tell you later what is the physical meaning of omega b tau. I just tell you that when the magnetic field is 0, omega b is 0, and so this two term vanishes, and we have only the term parallel to the temperature gradient. And this term is pretty easy to be interpreted because basically it's the one that appears in a Fourier equation that we study in elementary courses, and basically the heat flux is proportional to the gradient of temperature. So this first term is pretty easy. How does inserting a magnetic field changes the picture? Well, in the following way, we know that in our case, the electrons are the main heat carriers, and the electrons are charged particles. And when we have a charged particle experience a Lorentz force in a magnetic field, that force it to move in a liquidal motion around, again, its center, we say around a magnetic field line. And so the motion is not perturbed in the direction, is free in the direction of the magnetic field line, but is strongly constrained in the direction of orthogonal to the magnetic field line of the sides equal to the Larmor radius, which is scales inversely to the magnetic field. And here we see what is the role of what is actually omega b. Omega b is the zero frequency of electrons, which is a linear function of the magnetic field intensity. So these allow us to understand why the magnetic field have an impact on the thermal conduction, because basically, since the motion of electron is constrained across the magnetic field, also the thermal conduction is hampered across in the direction orthogonal to the magnetic field lines. In particular, the first term of this equation represents this orthogonal contribution to the heat conduction, and we see that it is suppressed by a factor omega b tau squared when this omega b tau is much greater than 1. While the second term represents simply the projection of the gradient, the temperature gradient, on the direction of the magnetic field. So it's this term basically recover what happened in the isotropic case. So in the direction of the magnetic field lines, we have the same condition that we have in the isotropic case. So this term does not depend only on omega b, but also by tau. What is tau? Well, tau is related to the collision and is the characteristic time between one collision of an electron and the subsequent collision with other electron or of another particles such as ions. And what is the effect of collision? The effect of collision is the following. Basically, the effect is to disanchor the electron from the field line and to make it jump to another field line, to another guiding center. So it works in contrast to the constraining effect of magnetic field. And when we have the collision are very frequent, tau zero becomes approaches zero, so becomes very small. And we see that basically the parallel term vanishes, and the Fourier term, the first term basically becomes equal to the isotropic case. So really the collision have an effect which is opposite to the constraining effect of the magnetic field. And so a case in which the number omega b tau is much greater than 1 indicate a situation where we have many gyrations per collision, while the opposite case, we have many collision, let's say, per gyration. And what happened, what about the last term? The last term basically dominates in a situation when this number is of the order of unity. This means that physically that the magnetic field is not strong enough to constrain very strongly the motion of the electron, but is not even irrelevant, and the effect is the one of deflecting the motion of the electron. So basically this introduces a further component which is orthogonal to both the temperature gradient and the magnetic field. Okay, I want to go more in deep inside the code to solve this equation numerically. We discretize it. And now we need to choose a scheme to solve it, and we choose an implicit scheme. The idea is that the flux and the sources are not calculated at which are function of temperature are not calculated at the current time step, but at with the temperature at the next time step. We choose an implicit scheme because an implicit scheme is optimal to deal with stiff terms that are expected to appear in the source, namely the fact that the source have a very steep dependence on, especially the neutrino emissivity, have a steep dependence on the temperature, namely the neutrino emissivity. For many processes, the neutrino emissivity scale at the power 8 or the power 6 of the temperature. So choosing an implicit scheme is an optimal solution. This means that we can rewrite the system as the equation as a system, a linear system of algebraical equation, where the unknown variable are the temperature of each cells calculated at the next time step. So in order to find the solution for the next time step, we need just to solve this system. This is something difficult, but we can do it with a public library called the LAPAC. And I want to spend a few words about the grids that we use, because this grid is really particular. We use a grid called the cube sphere grid that was presented in this paper by Ronchi and collaborators in 1996. Basically, this grid is formed by 3 coordinates, 1 radial coordinates and 2 angular coordinates, and the spherical, constant spherical surfaces are basically constructed like this. Basically, the spherical surfaces are divided in 6 different patches, and we can think of this like thinking of a cube with 6 different faces, which is inflated until it reaches the shape of a sphere. Why this grid? This grid has two desirable features. First of all, possesses a radial coordinate, which is good because many quantities of the problem have spherical symmetry. And then it's non-singular, in contrast, for example, with spherical coordinates, which have singularities along the axis. And the price to pay to have these two features at the same time is that the grid is not orthogonal anymore, as you can see. And this makes the equation much more difficult, as you can expect. But we know that using this grid is something, even it complicates the problem, it is something feasible, because this kind of a grid has been already used in the past in other kinds of codes, for example, in GR codes, in atmospheric codes, and also in magneto-hydrodynamic codes. So we were quite confident that we can use this kind of grid also in our problem. Okay, I can skip this. I want to start presenting you some tests. The first test that I present you is the so-called Hotspot test. This is a qualitative test that is designed just to check if the interfaces between different patches in the grid, where, for example, angular coordinate change direction abruptly, does not introduce any pathologies and any undesirable feature in the solution. So to check if the grid is working correctly. Basically, we take a star, which actually not a star, a ball of a uniform material, because at the moment there is not any microphysics characterizing it as a star. It's just a ball of uniform material. We take it at a constant temperature, and we put a volume of the sphere at an higher temperature, and we want to see how the heat diffuses. And this is what we obtain. As you can see, notice at the boundary between patches, everything seems very smooth. And this is something promising, and we can see it better in this other plot, where I show you at a constant radius the temperature profile, at a constant radius at a constant time. Here, different color represent the point of different patches. And as you can see, the solution appears very smooth at the patches interfaces. If there are any discontinuity pathologies, we are not able to spot them. Now we want to move toward a more, let's say, quantitative test. We took this test from this paper by Perez-Azorin of 2006. And basically, this is a test where an analytic solution is known, so we can compare the analytic solution to the numerical solution. The analytic solution is known even in presence of the magnetic field, but we want to start with a case with the magnetic field is zero, so we want to observe an isotropic heat diffusion. And so we have this ball of homogeneous material, and we choose an initial analytical profile, which is a radial profile, which basically has a Gaussian-like shape. And we let the system evolve with time for more than 2 thermal diffusion timescales. And we see that after 100 time step, the numerical solution is almost perfectly overlaps with the analytic solution, which is something really good. But we can see it in a more quantitative way here, where what I show you is the average L2 measure, which is basically a sort of weighted average of the square of the relativistic error. Inside the computational domain, the relative error, of course, between the numerical and the analytic solution. And as you can see, this number is lower than 1. and it increases at the beginning of the simulation, but it saturates very fast, more or less after one diffusion time scale. And yes, and it saturates, which is something really promising. And this simulation is done with the resolution of 20 radial point and 7x7 angular point per patch. Then we switch on the magnetic field. And this magnetic field is a magnetic field orientated along it's a uniform magnetic field, of course, and it's orientated along the zeta axis. As you can see, the solution is no more a spherical symmetry, but as a cylindrical symmetry. And here I report the L2 measure for 3 different resolutions, where we basically in each of this run, we double the number of angular points. And we see basically that in any cases, the L2 error is lower than 1, and there is and we gain a sort of factor 8 each time we double the resolution. And this is the solution represented in a 3D plot. I show you because I think in this kind of plot you can see very well how the heat diffuses according to what I was describing in the introduction, namely the magnetic field is in this direction, of course, and the heat diffuses very efficiently in the direction of the magnetic field, but in the direction of the magnetic field, the diffusion is strongly suppressed. And this is the last test that we perform concerning this set of tests. Basically, we changed the orientation of the magnetic field, first orientating them along the y and z axis, and then along the more arbitrary direction, namely toward the corner of the edge between 2 patches and the corner between 3 patches. And this is the L2 error, which is of the same order. As you can see in the cases of the field pointing toward the axis, the 3 runs have an overlapping solution, which is very good. Now we want to move. I want to show you some run which resemble more a realistic neutron star. But before doing it and concluding the talk, I need just to state what are we actually simulated of a neutron star. So what our computational domain covers. Basically, we simulate in very detail the crust of the neutron star. We also simulate the core, but we simulate the core only with 1 cell. So in our code, the core is described only with 1 cell. The reason why is that the thermal conductivity of the core is much higher than that of the crust, and so the core, except in the first decades of the life of a neutron star, is almost always in isothermal state. We don't simulate the envelope because in the envelope, the gradients of the physical quantities are much more steep, are much steeper, and the thermal relaxation time is much smaller. So it's prohibitive to simulate both the crust and the envelope. And instead, we employ some static model of envelope to link the temperature at the surface at the envelope to the temperature at the base of the envelope, namely at the interface between the outer crust and the envelope. The core evolved according to this equation, where basically we neglect the contribution of the flux of it between the core and the crust. And we consider only the neutrino cooling of the core. And on the other end, concerning the external boundary condition, we simply state that the flux at the boundary between the outer crust and the envelope is equal to the flux that the envelope radiates through black body emission. So these are our internal and external boundary conditions. And now I show you a run that is more similar to a realistic run, even if, so this object now almost resembles a neutron star, even if the microphysics that we are taking into account are is not very realistic. We consider here a magnetic field which has a dipolar colloidal structure with a magnitude at the pole which is of the order of 10 to the 14 Gauss. And we consider a crust and a core with a uniform temperature of 10 to the 10 Kelvin degrees. We consider a uniform profile for the magnetic diffusivity and also for the number density of electron. We consider only one process of neutrino emission in the core and modify the Urca processes. We don't consider neutrino cooling in the crust. This is not realistic, especially at this high temperature. Our code is designed to consider neutrino cooling in the crust, and also in the present implementation we can do it, but I decided to switch it off because I think that the solution is more easy to be interpreted in terms of heat diffusion. And another point is that the microphysical quantities such as the heat capacity per unit volume and the thermal conductivity are described by some simple analytical formulas. And moreover, I consider only the electron contribution for these two quantities. This is very not realistic because we know, especially for the heat capacity, that the neutrons, especially in the core and the inner crust, are the dominant contributors. So, given this introduction to the simulation, I show you this result. We have a phase where the core cools unrealistically rapidly, and then we have you should start to see the heat diffusion through the crust. And if you remember that the magnetic field is dipolar, you can see that the diffusion is more efficient here, where the magnetic field at the pole, where the magnetic field is parallel to the temperature gradient and is basically very inefficient here at the equator, where the magnetic field is orthogonal to the temperature gradient. So basically, the solution of the final state of this run is the creation of a sort of hot equatorial belt on the surface of this neutron star. Now we do something a bit more realistic using a non-uniform profile for this quantity eta and the magnetic diffusivity, namely, and the number density, electron number density. In particular, the electron number density is increasing, going toward the center, and this is what we obtain where we change this profile. We see that the evolution is more isotropic in the thermal diffusion, at least at the beginning. But when the cold front, the cooling front reaches the surface, you start to see some effects similar to the previous run, namely the heat diffuses more efficiently in the polar region than in the equatorial region. And the reason why you can see it if you look at the profile. These are radial profile of the term omega b tau. This is the profile, a radial profile at the pole. This is a radial profile at the equator. And as you can see, for small radii, we are in the regime where basically omega b tau is small, so is smaller than 1. So the heat conduction is almost isotropic, and we become dominated by the anisotropic term only when we arrive at the surface. And probably this is an effect due to the fact that the number density is increasing while we are going inside. And so basically this conclude my talk. I just want to summarize a bit what we achieved so far in the development of this code. Basically, at the moment, we have two different codes that are both working for the magnetic evolution and the thermal evolution. My part was concerned the thermal evolution, so I only mentioned this part. And they work in this very complicated cubed sphere geometry. And now we have implemented also a simplified microphysics, which is described by simple analytical formula. They are the case of the run that I showed you before. And in the last week, thanks to Daniele's work, we have also a more detailed realistic microphysics that exploit a public code written by Alexander Potekin that exploits some tabulated models for the microphysical quantities such as the heat conduction, the heat capacity, and the neutrino emissivity. And also last week, we performed a coupling between the thermal and the magnetic evolution. So in principle, now our code can run in both the thermal and magnetic evolution at the same time. So basically, what are the next steps? We just need to test more the code, test in particular the microphysics, the realistic microphysics, and then we just need to parallelize the code because, as you can imagine, dealing with the 3D code, it's very convenient to have it running in a parallel mode. But concerning this point, this kind of task will be assigned to a computer engineer that will do it for us. Before concluding, I just want to mention that at present in the market, there is only one code that is able to study the magnetothermal evolution of neutron star in 3 dimensions. This code is called the Parodies and is an adaptation of a code that was initially thought to describe planets. And these are some references for this code concerning neutron stars. So I want to state a bit some difference between Parody and our code. First of all, our code is a finite volume scheme, as I described, while Parody uses a pseudo spectral scheme. And this is great. This is wonderful because it means that these codes are complementary. Finite volume scheme are more adapted to describe discontinuities in the solutions, while pseudo spectral scheme can take into account higher multiples in, for example, in the magnetic field configuration. While another important point concerning the microphysics, while we can exploit these tabulated models for the microphysical quantities, Parody code, this is more difficult for Parody, and Parodies now can use only simplified analytical formula for the microphysics. So we expect to be more detailed in this aspect. So basically, this concludes my talk, and thank you very much for your attention.
Thank you very much, Stefano. Very nice presentation, especially with all the videos, the simulations. Thanks for the broad introduction showing how the electron, moves along the magnetic field. Thank you. So are there any questions? You can raise your hand or just, yeah, okay, Aldo?
Yeah, hi, very nice talk. Thanks a lot. I have one question out of complete ignorance. And can you tell a little bit more what goes into the calculation of tau zero? So the time scale, I mean, when you mentioned how many collisions there are per gyration.
Yes, basically tau zero is something at the moment we choose a constant constant profile, but actually it should be. I'm not very expert on this part, but tau zero should be also related to other quantities in the problem, such that basically we derive this quantity omega b tau zero at once as a function of other basic quantities, such as this magnetic diffusivity here, and it should be related, for example, to the density of electrons and like this. From let's say an analytical point of view, I would say it is calculated starting from the frequency of a collision of every species presented in our structure. I don't know for sure how these collisions frequency are calculated. That's the point.
I have one other question, if possible.
Yes, of course.
Yeah. Okay. So you mentioned that at the moment you are not putting a realistic envelope because that would slow down the calculations by a huge factor. So you have a relation between the temperature below and on the surface, what you call the surface. So that's a local relation you are using. Is this correct?
Yes. Yes, yes, exactly.
Okay, so then my question is, since you were talking in the beginning about the hotspots that are observed or inferred at least through the pulsations and so on, how robust would be the identification that you could do in terms of the size, for example, of the spots to what is produced in your models? Because of course, if your relation is local, you are ignoring heat diffusivity along the surface, right? From a hot spot coming from below to cooler region. So this...
Oh yes. Okay, yes, that's a good point. I'm not very sure, honestly, about this aspect. It's I think yes, that's true. Our relation is yes, it's local, and well, I think that also in this case an important role are assumed by the magnetic fields. For example, not in the present implementation of our envelope, where we don't consider the magnetic field, but in other implementation that our model will have, there will be a magnetic field that, in case it's directing in the radial direction, it will strongly constrain the heat diffusion in this orthogonal direction. Okay. So that could be one point. Okay. I don't exactly know how this envelope model deal with the heat diffusion in the transverse direction.
Okay. And even in once the code is parallelized, this would still be not possible to be added an envelope there, I mean, as part of the simulation, or is that impossible really, or?
No, I think it's the envelope is still it's still in. It will still a local still imply a local relation. So in this sense, it's from a parallelization point of view, is not very.
That will not speed things up enough that you will be able to do more. Okay, good. Thanks a lot. Very nice talk. Thank you.
Any other questions? I have one minor question. Okay, and it's just in the simulation about the hotspots. What's the time scale? I guess.
No, the time scale are really not physical. So it's here is everything in a dimensional unit, all the microphysics, the radius. This is just a ball of constant material. In terms of let's say diffusion timescale, it's like the Perez-Zorin problem. So it's a couple of thermal diffusion timescales in our dimensional units.
Okay. Carlos?
Yes, thanks. Thank you, Stefano, for the talk. I just have a curiosity. But it's about this last thing you mentioned about this other code, this parody code that uses this spectral method. Do you know what kind of functions are they using? I mean, what the basic functions, spherical harmonics or something like this?
I don't know, honestly. I think spherical harmonics, but I don't know the details of this code.
Does it have any particular problem for this application, this code, or is it?
Well, I never used this code in particular, and another thing, the spectral, it's a pseudo spectral, so like the radial part, yes, it's so it's only the angular part is concern this. But for example, as far as I know, this code is quite difficult to apply this public code for the microphysics to the spectral the spectral code, because basically you need basically to calculate the transform of the macrophysical quantity, which is not something trivial. And so in our cases, it was much more easy to exploit this kind of public code.
I see. Thank you.
Aldo, did you have another question, or you still have your hand from before, right? Yeah, okay. Okay, so I don't see any other hands raised. So thank you very much, Stefano, then. It was very nice. Yeah,
thanks.
And see you all next week. Thank you.
Bye-bye.
Bye.
Thank you. Bye-bye.
Thanks a lot. Very nice.